Hello everyone, so for context I am making a laptop based on a compute module, and today I want to talk about my arch enemy, which is the display. The thing is, if you ever wanted to use like display like this, you probably realize that you need some kind of driver board like this, or maybe like this. These have one thing in common. They use Chinese chips you can find no documentations for, and they are often not made for purpose that you want to use them, I guess you can say. The reason for this is quite obvious. Some guy goes to the manufacturer and says, "Konnichiwa, I want to make, I don't know, 5 million of devices that will have these specs and I need to display for it." And they say like, $100, good? Yeah. And so 5 million of displays are born. Then maybe some aftermarket producers produces some, but at some point there will be stock of these displays that will be like unused, and some other guy then says that, hey, I got like 50,000 of these displays and I cannot sell them. What shall I do? Well, here's an idea. Let's make a driver board and sell them to general public. And so the specs for the display are next to non-existent. The specs to the driver boards or the chips are next to non-existent. Like there is this like Toshiba chip that you can even program. I mean, even this chip you can program, but you have to sign NDA because I guess fucking HDMI, fucking whatever, they probably have like data from the manufacturer of these displays with some code, so you don't even have to program it. You just, hey, give me the code, sign this NDA. Yeah, sure, fine. You have the code, go ahead. Anyway, what's my point? Yeah, so things are getting more integrated. For example, the module that I'm using, this Raspberry Pi 5, has integrated MIPI drivers. It's not suited for this display because I need a dual 4-lane driver. This has two 4-lane drivers that cannot be synchronized apparently, so that would not work. Apparently, nobody probably tested it. So you could omit this driver board technically, but you need a driver for the display then. As I said, NDAs and stuff like that, I'm not dealing with that. Like, there is no point. And in my case it would be more reasonable to use HDMI anyway, because this way I have to route like, I don't know, 9 signal wires basically, instead of 16 plus much power lines to basically communicate with this display directly without any driver board. So anyway, what's the problem with this display driver then? Well, mostly the thickness. I have calipers here. If I measure thickness of the connector, this is 8 millimeters nearly. That's very much. But of course, let's say you don't use this connector because that's unreasonable. Let's say you want to use something more compact, something like this connector. Well, this is 3.7 millimeter. That's not great still. So what's the next limiting factor then? I guess components. 3.3 millimeters. We are getting there, but like this display is 2 millimeters. What's the point of having such thin display when this driver board is so thick still? So obviously you need this chip. This is the display driver itself. It is 0.7 millimeters tall, and this board is 1.6 millimeters tall. So how about we use 2-layer 0.5 millimeter board instead? This could technically get us to 1.3 millimeter thickness, which is quite nice. And so there is a path forward for a slim solution, but obviously you cannot. You can replace few components here to be low profile, but you cannot replace the board itself, which means you need to make new board. However, there are a few problems with that. For example, what is this thing doing? Like, we can, I guess, probe the pins. What I have done is just desoldered it and powered it on. It worked. Kinda, sorta. You see, this driver board is not working well even in its original form, but more about that later, I guess. So anyway, so this is obviously not really needed. This chip is probably USB-C decoy. So okay, so now I know that this part of the board is like unnecessary. However, there are a few weird things going on here. Let's zoom a little bit closer. And by weird things, I mean there are a bunch of these SOT23 transistors, like here's one, here's one, here's one, here's two. There's awful lot of them actually, so what the fuck are they doing? Like obviously there is one that is driving LEDs. What is this regulator doing? And things like that, so... And I can tell you right away that if you would probe these components, you would have still no fucking idea. Because honestly, I think what happens does not make much sense. So I watched some YouTube video where a guy talked about reverse engineering Raspberry Pis actually, but basically he said that like caveman method was sanding this board and revealing the copper, and he was talking about like X-ray tomography, so I was like, sanding the board. And so that's what I did. This was 4-layer PCB. I have sanded 2 signal layers. This is a bunch of power islands, which are honestly... Wowee! Who designed this board? This was fairly time-consuming and messy process, but if I did not do this, I don't think I would be able to reverse engineer this board completely and accurately, I guess. Anyway, so I will transition now to the screen recording and I will continue there to explain how I did few things. So here you can see a bunch of... whatever is this? Bunch of photos that I have taken. These are like adjusted to fit the same rectangle basically. I have done this in GIMP. Oh, this is finished schematic even. Anyway, I will get to that I guess. So this is how the thing looks in GIMP, and here you can do things like this, for example, so you can change the opacity and you can see that there is transistor that goes from here, then you can hide this layer and you can see that it is going to here. The alignment is not perfect, but it's like very obvious what's going on there. As you can see, this is just one big ground plane. This is layer 2 and I have moved it to the very bottom because like if there is nothing going on in layer 1, 3 or 4, you can be sure that it goes to the ground. And even let's see, for example, this LED. So this goes through the layer 1, it goes through the layer 3, and finally it goes to the layer 4, and layer 4 has also some ground planes. Well, actually only plane on the layer 4 is ground plane, so you can be sure that that pin goes to the ground, or that pad I guess. Another thing that I have done is I have gone to layer 4 and I manually marked the tracks going on the layer 4, and this is on the transparent layer, so I can just disable layer 4, enable layer 1, and now I can see what goes where. And finally there are a bunch of buck converters here and one boost converter here. I basically wanted to know how this whole thing is wired, and there is some funky stuff going on. For example, there are a bunch of inductors. Looks like it's to suppress the high frequency noise, but like, is that really that necessary? Like, look at this shit. Like, these are all bypass capacitors. Like, I think that would be good, but I don't know. So if you look at layer 3, there is a bunch of stuff going on, and to make my life, I guess, a little bit easier, I've created this layer, which I have applied a bunch of filters and bucket filled this thing with different colors. I should have used much more different colors than they are here, but it is what it is, I guess. So now what you can do is you can go to first layer and you can zoom out to some buck converter. For example, this one I have already did this, but basically what you can do, like, where is this coming from? Well, you can hide this or make it a little bit transparent, and you can see that this is connected to this plane, this plane, this to this plane. So you grab color from this layer and put a dot here basically, and then you can bring out this layer, and if there is, let's say, where is a good example for this? Yeah, for example, this is connected to this plane, so you can propagate the color closer to chip, so you have like easier time deciphering whole mess here. Then finally, as I was putting components to the schematic, I created new layer and marked the components that I have already like put on there. Now either components or signals that are marked red are basically things that I did not include there, and this white is something that I should have included there, but either I forgot or I did not save the file. There is one oddity, one very big oddity. So here is a resistor R33, and so where is this resistor going? Well, it is here, but is there any hidden via under this layer? So let's check layer 3. No, there is no via. Let's check layer 4. Nothing there. Maybe layer 2 even. Nah, there is just copper. So this resistor goes absolutely nowhere. So, you know, also if you look at the power plane, there are very funny things going on. Like, for example, there is track from here to here, but the plane is already here. Like, you know, you could like put track from here to here, for example, or maybe this plane, it is connected to here and to here, to here, to here, to here, but then nowhere else, and there is track from here to here, while this could be connected directly. Like what the fuck is going on here? Like, there is a connection here, but then there is nothing. So, and here you can see this ground plane, and this pin is also grounded. Like, why is this copper not connected? Like, what's the reason for that? Why is there island that is filled and this not here? Yeah, this is very weird board. Anyway, so I can show the schematic. I guess first of all, the most like interesting thing is the power management, I guess. So there are these buck converters, and these are labeled as the voltage should be, not as it is. For example, this 1.8 volt rail was almost 2 volts. Now if you look at the datasheet for the display, the 1.8 volt is like, it should be between 1.7 and 1.9 volts, but it was definitely larger. However, I have checked for this, and the absolute maximum rating is nearly to 5.5 volts, which is interesting. As I was drawing this, I have marked these power lines by the color from the image basically that I have created. It is not very helpful, but it's hard to compare colors close together like this, but it's too many colors anyway, so you cannot do much. Anyway, so first buck converter, there is not much going on. I forgot to ground these chips. The second converter has a signal, enable signal. So there is this funny setup, and this open jumper means that there was no resistor on the board, which means that with this setup, this transistor is always conducting regardless of the level on this line. So that simplifies things. Basically, you can remove this whole thing and it will perform the same. Finally, there is this boost converter setup. It's pretty standard stuff, I guess. There is this funny setup here. This drives LEDs, current goes back and sinks to the ground. So this pin measures the voltage, and there's a label that this looks like constant current LED driver. In the newer version of this board, you can control the brightness of the backlight, so I assume what happens is this is driven with pulse width modulation from the chip. It could be that this board has also this capability, but the buttons were not on the board, so I did not test it. Now this is also quite funny setup here. There is 5V input to the whole board, and it is not enabled by default. It is enabled only if HDMI has been connected, and this is done basically by getting 5V from this HDMI. For some reason, it is dropped down to 1.2 volts, and then via level shift this transistor is closed or open. Now if you look closely at this, this design is retarded, and as I said that the signal is level shifted, well, it isn't, because there is no pull-up here. So basically this can be only at ground or ground. So this transistor is always conducting, it's just sometimes it's conducting a lot, sometimes not as much. So, and I can confirm that when I plugged in this board, the 5V, both LEDs were lit. It's just one was quite dim until you plug in the HDMI. Here's this thing, this is implemented properly at least. This is a level shifter for HPD line on the HDMI. Alright, so here's another funny setup. So first of all, this is LCD reset signal, and so this transistor Q6, it is driven by the HPD signal for some reason via this resistor. I guess, fine, whatever, you do you. So if this can pull the line low, basically. There is pull up, and there is another transistor connected to GPIO5. There is only GPIO5 anyway, but this can also pull the 1.8 signal to ground. However, this is driven by 3.3 volts, and what's the difference between 1.8 and 3.3? Not much. So even if this is high, like the difference between the two voltages is so low that this transistor will always be conducting. And so this is draining current from this resistor, which means that this reset signal never goes to 1.8 volts fully. So here is how this looks on the oscilloscope. The yellow line measures the GPIO5, which is gate of Q4. The orange line measures gate of Q6, which looks very sketchy, and the blue line measures 1.8 volt line. When I look at the LCD datasheet, here is power on sequence, and it is visible here that reset should go low, then we should wait, then we should release reset so it goes to high, then from high to low again, and then from low to high again, which kinda sorta looks like on the picture from the oscilloscope, but there is one problem. So again, blue line is the reset signal. Look at the oscilloscope image, now look at the schematic, and tell me what can possibly cause the blue line to produce the first pulse. There's only one solution. This 1.8 volt line must go high and then low, which would be great. However, this line is the same thing as VCC for the LCD, and therefore the first pulse means absolutely nothing, and somehow this works. However, there is this nice graph, so reset timing at power supply on, IOVCC goes up, and then sometimes later reset goes up too. And so initial condition, default for hardware reset. So what the fuck is correct now? Is it this thing or is it that thing? I mean, it works, so likely this is fine. Also look at this 1.8 volt buck converter. Does it have anything on the enable? No. So how the fuck does it do the first pulse? I cannot imagine anything else than something messes with this 5 volt signal, because I have no idea, man, I have no idea. Maybe this transistor, what the fuck is this transistor doing? Nothing, because it's not connected to the display. My theory is that there is this this is the green board, the small one that I showed in the images, I guess this one, which is interconnect from the main driver board to the display, and I guess they have a universal driver board and many of these interconnect boards. On this board is a little charge pump chip, which is creating plus and minus 5.6 volts for the analog stuff on the display. And so with this I should be able to create custom board that uses this chip. I will probably replace chips for buck converters and boost converter as well, obviously. I will remove much of the weirdness here. This chip also needs power sequencing from the datasheet, but like there is one sequence, this 3.3 volt line basically, and I think it needs 3.3 volts before 1.2 volts, but I'm not sure. I know, let's check, I guess. Yeah, it needs 3.3 volts before 1.2 volts, so what the fuck are these guys doing? It needs a delay on the reset line. Oh, wait a second. What if it is doing this? This is system mode. Huh. That's interesting. I need to measure this because I did not measure this with oscilloscope, but question is whether this will be question is whether this will be obeyed, I guess. The reset of this chip has at least some RC circuits, so there may be some delay generated by this. And as I've said, this board barely works. Like, I get a bad image when I power it up. I suspect what is going on here is the value of this resistor is too high. Actually, I have a list with the passives 1.5k. Okay, so you cannot go much lower than this. I could try maybe 200, maybe 300 ohms and see if this improves the situation. Other than that, the incorrect thing would have to be sequencing, which I would have to desolder this transistor and put in their manual like button. Also, this transistor probably does not help either. I would desolder this one maybe. I don't know, I would have to try this.